The first and primary is unbalanced forces present in the machine. So these forces may produce vibrations, and then the elastic nature of the system. Self-excitations also produce vibration due to friction in between the two mating surfaces, and then external excitations or external forces may cause vibration. So obviously the next two, I think you all know that wind. When you ride two-wheeler on road, I think definitely you might have experienced during monsoon period and all. So winds may cause vibrations in certain systems or transmission telephone lines and all certain conditions. I think you all know that. Earthquake. So earthquake also cause vibrations and are greatly responsible for the failure of the dams, many buildings. So earthquake is a very, very dangerous one. I think that time a huge vibration we may experience. So that is a very, very dangerous one. The extreme case of vibration is called earthquake. I think we all know that. And then there are two effects are there. One is negative and then positive effects. I think you all know that when vibrates, when a machine number or other things vibrate, what will happen here? Definitely it produces unwanted noise, high stresses, wear, poor reliability. So which leads to premature failure of any one of the parts in the guys. You are all sitting under fan. It's smoothly running, you know. If any sound comes, what I think immediately comes into our mind, you know. So we have to immediately replace the bearing which is available in the fan. So the effects of the negative effects of vibration is very, very very, very important because it starts from noise. So finally it produces premature failure of any one of the part. So any one of the part in a machinery or a mechanical system fails, the whole mechanical system is completely get damaged. So to avoid that, we should carefully keep on watching the various rotating and reciprocating parts available in the mechanical system. So even some of the positive effects are there, even though it has some harmful effects. I think you all know that musical instruments, so guitar and all, we are playing with the guitar and all, and also you might have used ammeter, a voltmeter to measure voltage and ampere. So these are all the instruments are positive effect of. Definitely we need some vibration to show, you know, in voltmeter, ammeter and all, the needle deflects and then it shows the voltage, the corresponding voltage. So how it happens? It's due to vibration. Definitely we need vibration to some extent to measure the voltage or ampere. So similarly, if you want to play a musical instrument like violin, guitar and all, definitely we need the same way vibrating conveys, vibrating screens, shakers, vibrating bowl feeder. So in physiotherapy and all, I think physiotherapist uses a vibrator to relieve pain and all on our neck pain, shoulder pain and all. So physiotherapist mainly using this kind of vibrating vibrators. So some of the positive effects also there, even though it has some negative effects. So how we can eliminate that? What is the main aim of studying vibration, guys? I think the main aim is to. What is the main aim of studying vibration? Definitely you should know. As a design engineer, you must know what is the main aim of vibration. So resonance you might have studied in your physics in 11th, 12th physics you might have studied. So it's an undesirable phenomena. Resonance, I think you all know that it is an undesirable phenomena. So which leads to system failure actually. If vibration more in a system, mechanical system, it leads to failure. So in order to avoid resonance, actually a design engineer should carefully design a system with utmost priority given to ensure the frequency of the design system should not coincide that of its natural frequency. So that's why it's important to determine the natural frequency of the given system first. So that is the main aim. So a design engineer role is to avoid resonance in a system which is to be designed by him. That is to be that is to be carefully taken into account all the various factors which affect the system based on the parameters taken into account the system. So, what are methods of elimination and reduction of the undesirable vibrations? By removing the causes of vibration, by resting the machinery on proper type of isolators, by using shock absorbers. I think you all guys know that you are riding how your comfort is ensured in two-wheeler and all. Nowadays, you are having using very costly bikes and all, 1.5 lakh, 2 lakh bikes and all you are riding. So mainly depends on your comfort and all. The riding comfort and all depends upon the shock absorber. Mainly, you guys are very well aware of that. So shock absorber is a very good um, one to avoid or eliminate. We cannot completely eliminate vibration, guys. It's very tough. We can minimize. We can minimize so that then only you can ensure the reliability of the mechanical system or any other part which is available in the machinery. So by providing screens, if noise is the objection, so I think in theater and all, screens are placed to avoid echo and all. So otherwise echo will come. So these are some of the methods to eliminate or reduce. Okay. And then these are the very important terminology used in vibratory motion. You should definitely know, guys. Periodic motion. What is periodic motion? What is time period? What is cycle? What is frequency? What is natural frequency? What is amplitude? Resonance and damping. These 8 are very important. So, guys, if you want to do any experiment, you must know these basic concepts, basic terminology. If you want to solve any gate questions and all in future, definitely you must know. It seems very simple, but when you attack a problem, when you attack your university problem or any gate question and all, definitely all your conceptual part and all starts from this terminology part. I think many of the guys are don't know what is resonance. Still, I think many of the guys don't know about natural frequency, what is amplitude and all. If you are thorough with these 8 terminology part, you can easily attack problem also. So one more thing I want to tell you, the first half of your third unit, damped longitudinal free vibrations to be carried over to fourth unit also, forced vibration. So the same formula is to be used in fourth unit also. So first you should thorough with the terminology part. Hope you all have done few experiments with the help of you would have used these formulas, some of the formulas in your experiments also. What is time period and all, experimental time period, how you can calculate, experimental frequency, how you can calculate and all. So let us start with periodic motion. A motion which repeats itself after equal interval of time is called periodic motion. Time period is the time taken by motion to repeat itself is called the period of vibration. So if the motion completed during one time period is called cycle. So periodic motion, it's a regular, and then time taken is time period, and the motion completed during one time is called one time period is called cycle, and then coming into a very important term, frequency. So number of cycles completed in 1 second is called frequency. So normally it is expressed in hertz. Normally it is expressed in hertz. Actually, the unit of frequency is hertz. So it is nothing but a reciprocal of time period. So F equal to 1 by time period. So natural frequency very important. Just to clearly differentiate, what is natural frequency? Frequency of free vibration of the system is called natural frequency. I'll tell you later what is free vibration. So amplitude, this is very important. Amplitude or displacement. The maximum displacement of a vibrating body from the mean position. I already told you, when you take a spring mass system, so once you pull it now, it displaces from its mean position. So how much displacement takes place once you disturb the vibratory body? So that is called amplitude. Don't get confused with amplitude and the maximum displacement. Displacement is nothing but displacement. Yeah. Once you disturb the system vibratory body, it moves from its equilibrium position to extreme position. So that displacement is called amplitude. Our main aim is to reduce this amplitude. So what is the purpose of within the 2 lines I will brief about vibration. If you disturb or externally with the help of external force, if you disturb any system, it vibrates. If it vibrates, what will happen? So it may go from its mean position to large displacement. So if the displacement goes very large, what happens here? Definitely vibration. That system, I think, produces huge noise. Huge noise. I already told you one very important term called resonance. What is resonance here? So just look at when the frequency of the external force is equal to the natural frequency of the vibrating body, the amplitude of vibration becomes excessively large. So this phenomena, this term is known as resonance. That's it here. So if you want to design any, as a design engineer, what is your role in designing any mechanical system, take into account all parameters which is relevant to vibration? No, a system should not, a system frequency should not go to the near the value of resonance. It is to be designed. It is to be designed below its resonance values. That's right. So the external frequency, external force frequency matches with vibrating body frequency. Definitely, both will. Tamil நீங்க படிச்சிருப்பீங்க ஒத்ததிர்வு. I think probably Tamil medium guys, I think you all know that ஒத்ததிர்வுனா. So both will match at a particular frequency. So that may lead to breakage of the system. So that may lead to premature failure of the system. What is premature failure of the system? I think you all heard about premature baby. So a baby born at after fully grown baby, I think it's born, it gives birth at 9th, 10th month. So if it born pretty early, 7th month, it's called premature baby, preterm baby or premature baby. Likewise, a machine or mechanical system life is 10 years. So due to vibration, due to recurrent vibrations and all, leads to premature failure. So within 5-4 years, I think it may, this entire system may get damaged. Okay. What is the next term? Last, damping. So I already told you, when you disturb, when a vibratory body, if it is disturbed by external force, it vibrates, and then amplitude is more, and then it displaces from its equilibrium position to extreme position, and then it's vibrating, so it produces noise. So you should not reach resonance. So what we have to do here? So we have to reduce this vibration. We have to reduce the vibration. We have to reduce the amplitude or displacement of the vibratory body from its equilibrium position. So what we have to do? So we have to provide dampers. So dampers, so which is a very important device which helps to reduce the decay of the oscillations in the vibrating body. So that phenomena is called damping. The resistance offered by the damper to the motion of the vibrating body is called damping. We are going to see in detail after the next things. Okay, so these are the very important terminology used in the vibratory body. So this is very, very important. So most of the vibrating systems follow simple. We are going to assume. So most of our vibratory systems follow simple harmonic motion. I think if it moves with a particular position, mean position, and then its acceleration is always proportional to its distance from the mean position and is directed towards the mean position or equilibrium position. So you don't go in depth and all. So a vibratory system is assumed to undergo a simple harmonic motion. That's it. Just look at a particle P moving around a circle with uniform axial angular velocity omega, and then that is to be given as finally a fundamental or differential equation of simple harmonic motion given as d square x by dt square plus omega square x equal to 0. I think you all guys know that every physical phenomenon in the world can be represented with the help of mathematics and physics. So engineering is an applied science. You all know that, guys. Engineering is an applied science. Without maths, physics, you cannot do anything. So as a mechanical engineer, you should be strong in physics as well as mathematics. So all physical models are to be finally converted into differential equations or governing equations. So all the analytical formulas and all how they derived, guys, with physics and maths. So mathematical concepts and then physics principles are definitely used. So I don't want to go in depth. So displacement of particle from its mean position after time period t, it is represented as x sin omega t. So that is to be finally given as d square by dt square plus omega square x equal to 0. I think you can refer 3-step derivation. You can refer R.S. Kurmi, theory of machines by R.S. Kurmi, S.S. Ratan and all. So I don't want to go in depth of deriving all the equations and all. So from this fundamental equation or differential equation of simple harmonic motion, we can arrive at time period of the vibrating body, Tp equal to 2 pi divided by omega. And then frequency of the vibrating body can be written as 1 by Tp, that is the reciprocal of time period, or omega by 2 pi. So this is the basic formula. From here we can start all arriving, we can derive other formulas. So this is the most fundamental differential equation of simple harmonic motion. From that we can derive time period and frequency of the vibrating body. So now we move on to types of vibrations. So types of vibrations. So vibration can be classified into two types actually, according to the actuating force and then according to the stresses in the supporting medium. So first one is according to the actuating force on the body. So free or natural vibration, forced vibration. So free or natural vibration again classified into two things, damped and undamped. Forced vibration again classified into damped and undamped. So vibration according to the stresses in the supporting medium, longitudinal vibration, transverse vibration, torsional vibration. Guys, all of you listen here. Here a very important point I want to tell you. Your third unit actually mainly we are going to start with free vibration. Free vibration. What is free vibration here? If any initial disturbance given to a vibrating body, it oscillates and then it comes to rest position after some time. So simple pendulum, just take a simple pendulum, just you just push to it and then it oscillates and then comes to its original position. Or so similarly, forced vibration under the influence of external force, under the influence of, so continuously a force is, external force is acting on the body, which leads to forced vibration. Now, so our third unit mainly deals about free vibration only. Free vibration. So this free vibration also has two classification. One is damped, another one is undamped. So don't worry about undamped. I think what is damping? I already told you. The resistance offered to the motion of a vibratory body with the help of a device called dampers. So it actually helps to reduce the amplitude of the vibrating body during vibration. That's it, damper. So we are going to derive formula and all for free or natural vibration of a vibratory body with dampers. So undamped free natural vibration is not an issue here. But anyway, these are all simple problems. So I think an exam point of view, visit exam point of view, you can expect questions, 16 mark questions and all from damped only. So undamped, you can just go through. It's a simple problems. You can expect questions for your competitive exams and all sometimes. So mainly we focus on damped free natural vibration. So forced vibration again you are going to see in fourth unit. And then especially free natural vibration, free or natural vibration of longitudinal body we are going to discuss about. Okay, so what is longitudinal vibration? There are three different vibrations are there. I will explain one by one. So these are types of vibration. Okay, look at here. So what is longitudinal vibration? Just look at a shaft is there. So a mass is attached at the end of the shaft. Just look at the oscillation. Just look at the oscillation. The shaft vibrates, parallel to the axis of. So shaft has axis, and then the shaft vibrates parallel to the axis of the shaft. So this kind of vibration is called longitudinal vibration. So the next one, just look at next one. The shaft. What about the shaft oscillation? It is perpendicular to the direction of axis of shaft axis. Now look at torsional vibration. So twisting is there, no? The circular disc which is attached to the shaft is twisted either alternatively in clockwise and anti-clockwise. Right? That time a torsional shear stress induced. The corresponding vibration is called induced vibrations. So these are the three important types of vibration according to stresses in the supporting medium. So mainly we start with the longitudinal vibration, guys. So in your third unit, look at here. In your third unit, mainly deals about free natural vibration, mainly attached with the damper for a longitudinal body. So we are going to start with damped, undamped, free or natural vibration of a longitudinal body, and then damped, free or natural vibration of a longitudinal body. This is what we are going to see, and then we are going to derive formulas. Based on that formula, we are going to solve problems. So this is very important, guys. I think the free natural vibration of a longitudinal body with the damper is very important, because these formula and all you are going to use same formulas. You are going to use it for your forced vibration. So you should thorough with this part. So I think in unit 3, I think it has 3 different sections: longitudinal vibration, formulas, longitudinal vibrating body with damper, formulas, problems, transverse vibration, formulas, problems, torsional vibration. So mainly in university exam and all, if you thorough with these first 2, I think easily you can get marks. Why I'm telling to concentrate more on longitudinal vibration of vibrating body with the dampers, the same formulas can be used for your 4th unit also. So you thorough mainly the longitudinal vibration of vibrating system. So I already told you a basic vibratory system model can be with the help of, we can represent with the help of a simple spring and then mass. And then the various other elements also attached, mainly dampers also added in the vibratory model. So a simple vibratory model consists of mass, spring, and then damper, which arrests the vibration or which reduces the amplitude of the vibration of the vibrating body during oscillations. Let us start with, I already told you. Now we are going to start with free or natural vibration of a longitudinal vibration. Free or we are going to discuss free or natural vibration of a longitudinal body. Let us start with just look at here. So free or natural vibration of a longitudinal body. Is there any damper? Is there? I already told you damper is a device which is attached to the vibratory body, reduces the amplitude of the vibratory body. Damper attach பண்ணேன்னா அதோட வைப்ரேஷன் ஆக்சுவலி அதோட ஆம்ப்ளிடியூட் அதோட டிஸ்பிளேஸ்மெண்ட் குறைஞ்சிரும் இல்லையா? ஆம்ப்ளிடியூட் குறைஞ்சாவே ஆக்சுவலாக வைப்ரேஷன் குறைஞ்சதுன்னா நாய்ஸ் குறைஞ்சிரும். I think you can ensure the safety of the reliability of the machine. Just look at a simple pendulum. I already told you. Just if you give some initial disturbance, what happens here? So it oscillates, and then that green vertical line is called its mean position. It comes into rest. So there is no, instead of any damper and all, it comes to its original position. Just you give some initial disturbance or push, and then it oscillates for few cycles, and then it comes to rest. So this is called undamped free longitudinal vibrations. Guys, you understand here? I already told you what is free vibration. Free vibration is nothing but just you giving some initial disturbance and then you remove it. So it oscillates and then it comes to rest position. And then what about the vibration? It vibrates, whether it vibrates longitudinal direction or transverse direction. So the vibration takes place in parallel to the axis of this pendulum, So that's why it's called a longitudinal vibration. So now we are going to discuss about what are the various formula to be used for determine natural frequency as well as damped frequency of the vibrating body in a longitudinal body. So undamped means I think without any damping, there is no need to provide any damping at all here. So from I think so first undamped. I already told you this is exam point of view you should focus on. So here only few problems are there. So it's our elementary level problems. I think. So first, as I already told you, you should know what is the natural frequency of the vibrating body. So resonance, I already told you resonance. So you should know the natural frequency of a vibrating body. Then only you can avoid resonance. Otherwise, the excitation force frequency matches with the natural frequency of the body, which leads to premature failure of the system. So what are the various methods are available to determine natural frequency of undamped free vibration of a single degree of freedom spring mass system? I already told you a vibratory model is represented with the help of spring mass system. And then what is degree of freedom here? The number of input parameters required to specify the displacement or motion or configuration of the system. So in what about its motion, in which direction it moves? Normally if you take a structure and all, it has no movement in any direction, so 0 degree of freedom. So if you take a single spring mass system, if you pull it, what happens? It moves in only one direction, so it has only 1 degree of freedom. So degree of freedom tells about the mobility of the configuration of the vibratory body, in which direction it moves, x, y, z. So there are 3 methods are there: equilibrium method, and then Newton's method, and then energy method, Rayleigh method. So for your understanding, I think we mainly focus on equilibrium method. I don't want to go in depth. So already you studied in your unit 1 force analysis. D element principle you would have studied. The algebraic sum of the inertial forces and all external forces acting on the vibrating system must be equal to 0 to keep the vibrating system in equilibrium position. So if you want to ensure the stability of vibrating system, definitely all the vector sum of all the external forces, torques, and then the moments and all acting in the system should be 0. So based on that, a differential equation has been derived. So already told you fundamental natural frequency formula, from the fundamental equation of simple harmonic motion of a body, F1 equal to 1 by Tb equal to 1 by 2 pi square root of S by M. S is nothing but spring stiffness, M is nothing but mass of the body. If you take a single degree spring mass system, spring is represented with stiffness. So what is stiffness here? So the force required to displace the spring in a mean position to equilibrium position to extreme position, So that is called stiffness. So stiffness is nothing but load per deflection. So we can write in terms of 1 by 2 pi square root of S by M. So what is this S plus S into del equal to M into J? I'll tell you. So how these equations are arrived, guys? I already told you Newton's method or equilibrium method. So the name itself tells you equilibrium method. So this is your equilibrium or mean position. So when it is given disturbance, what happens? So what are the various? So this is your displaced position. This is your equilibrium position. So what about the displacement of the vibratory body? So here a free body diagram of the vibratory body shown here. So when you pull it, what happens? Gravitational force act downwards. Simultaneously, motion of the body acts up and down. So spring force, due to spring force, spring is there. Spring force act upwards. So when you pull mass, what happens? Gravitational force act downward, and then spring force acts opposite direction, and then inertia force also acts upward. So based on these things, we can equate upward and downward force. So So this is what here they have done, you know, upward force. So by equating upward and downward force, they finally determined this formula. A natural frequency of the vibratory body equal to 1 by 2 by square root of s by m. So yes, sometimes if by equating these two upward and downward forces, finally we can simply write the formula as g by del, gravitational force divided by deflection of this vibratory body. Again, it may be simplified as g is nothing but 9.81 divided by del. Again, it may be simplified as 0.4985 square root of del. So 1, 2, 3. So according to the, while solving the problem, I think it's sometimes this will be given. So which formula we can select? It depends on the data given in your problem. So you should not ignore. This is a fundamental equation. Sometimes you, for a simple problems and all, you may use this kind of this formula. Sometimes you may use this formula. Okay, guys. So the second method is not that much important, but anyway, you just understand. So based on energy method, assuming no damping is there in the system, the sum of kinetic and potential energies remains constant in the method. We can derive the formula to determine natural frequency of the system. And the third one is Rayleigh method. So this also tells about what about the maximum kinetic energy at the mean position, where the potential energy is zero, and which is equal to the maximum potential energy or strain energy at the extreme position. So based on energy terminology, also we can arrive natural frequency of the. So these two methods are not that much. We need not focus on that much for our exam point of view. So mainly you understand how the fundamental equations are derived based on analytical methods which are used. So now we are dealing about free or natural vibration of an undamped longitudinal vibrating body. So determine the natural frequency of a simple pendulum shown in figure, neglecting mass of the rod or equilibrium, mass of the body by equilibrium method and energy method. So these are the two simple methods given. Probably these kind of questions you cannot expect in your exam, guys. I think just for showing you how the fundamental undamped vibration of longitudinal vibrating body problems are solved under energy and the equilibrium method. Just look at length of the pendulum and mass of the mass which is attached. So based on equilibrium method, you all know that according to D'Alembert principle, the sum of inertia torque and external torque acting on the system should be zero. Then only you can ensure the stability of vibratory body. So that concept is to be placed here, and then finally you have to arrive a differential equation of this simple pendulum. So simple pendulum shown here. So when it vibrates based on equilibrium method, how we can arrive fundamental equation of the simple pendulum. Finally, this formula, same formula, we can arrive as 1 by 2 by square root of g by L, g by L. So likewise, use these methods, and then this kind of problems you practice it for your competitive exams, not for exam point of view. Similarly, energy method also gives the same formula, but we are going to take sum of kinetic energy and potential of energy is sum of these two energies should be zero, and then differentiate it, and then finally you will obtain differential equation method. Both same formula you can arrive. Okay, yeah. Now we move on to very important part of problem solving. So I already told you this is very important. I think this formula you're going to use in your problem solving. So I already told you a vibratory model is represented with a spring mass system. So here just look at here, two springs are there. Two springs irka. But this is actual system. What we are going to do, we are going to convert into equivalent system. So both spring stiffness can be converted into equivalent stiffness. Similarly, actually look at the springs are in series. If the springs are in series in a vibrating body, how the individual stiffness of the spring is converted into equivalent stiffness, and then what is the formula? So equivalent stiffness of the springs which are in series can be calculated by 1 by S equal to 1 by individual spring stiffness S1 plus second stiffness spring stiffness S2. So similarly, if you go for springs which are in parallel, no, S1, S2. Just look at in this vibratory model, both springs are in parallel and attached with mass. So we are going to convert into a single equivalent mass. So this is the formula. So these formula you must know, you must thorough this formula, just memorize this formula. We are going to use this formula in our problem solving. So I think you guys should know the concepts and then which formula you to select for. So each question has its own problem solving methodology. So you have to be very careful which formula, appropriate formula you have to select it, and then you have to solve accordingly. Okay, guys. Now we move on to very important section, damped free vibration. So university 16 mark or a section in the problem number. So far we have seen undamped free natural vibration, undamped free or natural longitudinal vibrations we have seen. So these kind of problems you may expect. Rarely you can expect an exam, but competitive exams and all, definitely you should know how to arrive at natural frequency of the body with the help of various methods given here, energy, equilibrium, Rayleigh. So while preparing IES, gate and all, you should know the basic formulas, how to derive equation and all. Okay, guys. Okay, and then we move on to damped free longitudinal vibrations. So what is damping? Already told you, the resistance offered by a body to the motion of the vibratory system. The device which is used for resisting purpose is called dampers. So the vibratory system which such dampers said to be under damped vibrations. So if any vibrating body vibrates with dampers, it's called corresponding vibration is called damper. So damped vibrations. What is the main advantage of damping? No, it controls the amplitude of vibration so that failure due to resonance may be avoided. Guys, you should remember these two lines. What is the purpose of studying vibration of any mechanical system? We should avoid the resonance. Then only, because what will happen, the natural frequency of the vibrating body as well as the external force frequency matches, resonance occurs, large amplitude may happen. So that leads to premature failure of the system. That should be avoided. So that should be avoided. Resonance. You guys should remember the purpose of studying vibration is to avoid resonance in any vibrating body. Resonance வரக்கூடாது எந்த ஒரு மெக்கானிக்கல் சிஸ்டத்திலையும் வைப்ரேட் ஆகும்போது ஒத்ததிர்வு அந்த வராம பார்த்துக்கணும். அதுக்காக தான் as a design engineer your role is very key role you are going to play. Just look at here, I will explain you. So in previous slides you have seen only spring and mass. Here damper we have. Here we have damper here. Actually what happens if spring mass is oscillates, what will happen? So it takes some time. It takes some time and then it settles down and then it comes into rest position. But here if we provide damper, there are various dampers and all that. I will explain briefly about what are the various dampers are available. So just it's a simple damper device which is attached with the spring mass system. Obviously it controls the amplitude. You can see it. Just look at the earthquake simulation is shown here on your left hand side of the video. Just look at here. What happens here? So here it's earthquake simulation on a structure is shown here. It heavily vibrates and then the box which is placed on the structure I think falls on. But look at the adjacent structure. What happens? It vibrates, but there is not that much vibration. It doesn't experience as the adjacent structure. Why? So here, just look at a support has been provided. This is called dampers. The supporting elements have been attached in this structure, which arrests the vibration, which arrests the amplitude of the vibration. So that's why it ensures stable. Somewhat, just look at. You can see. So the stability of the structure is ensured with the help of this kind of supporting elements called. Actually, it absorbs. It absorbs the energy dissipation is possible in this structure. So let us start with the types of damping, guys. types of damping. There are the various types of dampings are there, and then viscous damping, Coulomb damping, solid and structural damping, interfacial damping. There are 2 more questions you may expect. You can expect 2 more questions, right? Types of damping. So here we mainly focus on viscous damping. So continuously used damping mechanism is called viscous damping, actually, which is used to reduce the amplitude or displacement of the vibration. So when the system vibrates in a fluid medium like air, gas, water, or oil, the resistance offered by the fluid to the vibrating body, which causes energy to dissipate. So normally we are going to take viscous damping to explain all those things. So actually, it's an oil-filled damper which is moving in. So the resistance is offered by this oil to decay the oscillation present in the system. So now let us start with the various terminology associated with the damped, free or natural vibration of a longitudinal body. ஸோ என்னென்ன ஃபார்முலாலாம் இதில் டெரைவ் பண்ணலாம். ஆல்ரெடி நம்ம ஃபண்டமெண்டல் ஈக்குவேஷன் பார்த்துருக்கோம். ஒரு லாஞ்சிட்டல் பாடி வந்து டேம்பரோட வைப்ரேட் ஆகும்போது you don't bother about undamped vibration of a longitudinal body here. So our 16 mark question mainly comes into this topic. So what about damping coefficient? So the damping force per unit velocity. Actually, when vibratory model vibrates, so we mainly focus on this damper. The various terminologies are associated with damper. So let us start with what is damping coefficient. So we are going to mainly see about what are the important terminology associated with dampers. So damping force per unit velocity is known as damping coefficient. So it is nothing but is the ratio between damping force and velocity. And then if you provide, already we have seen when the springs are in series and parallel, what about equivalent spring stiffness? We have seen likewise, if the, just look at it's a simple spring mass system attached with dampers in series and then attached with parallel. Okay, how we can convert? So we cannot individually calculate. We have to convert into equivalent system. So how equivalent, C equivalent, guys, this formula is to be very important here. While solving a problem, you should calculate equivalent damping coefficient you have to calculate. C is nothing but equivalent damping coefficient. So how much damping resistance it provides to the vibratory body, that's it here. So எவ்வளவு தூரம் இது வந்து அந்த vibratory motion வந்து குறைக்குது, அந்த ஆம்ப்ளிடியூட குறைக்குது. கரெக்டா? This is the main concept behind damping dampers. So now we move on to formulas, how we are going to derive from fundamental or governing equation. Again, so in your previous slide we have seen what is the natural frequency of a longitudinal body without damper. Here just look at, we have attached a dashpot of damper. Now you just pull it. What happens? It displaces from its equilibrium position to this position. This x is nothing but amplitude or displacement. You just pull பண்ணி என்ன ஆகும்பா, இந்த equilibrium position இருந்து இந்த தூரத்துக்கு displace ஆகுது இல்லையா? But only thing, what is the difference between undamped and damped? Here damper has been attached, provided here to control the oscillations in the system. அப்படி ஆகும்போது same formula we are going to use, same procedure, same concept. What is the concept here? So this is free body diagram of mass at the displaced position. We have seen 3 different methods: Newton's method or equilibrium method, Rayleigh method, and based on equilibrium method by equating upward forces. Here spring force, damping force upward, and then most of the body acts downward. Inertia acts upward. Equate all these forces. Finally, we will arrive differential equation for spring mass system. So this is the spring mass system. So from this fundamental equation, we are going to arrive one by one. Over formula derive பண்ண போறோம். I think you guys should memorize all this formula. You cannot derive all the formulas. Sir, I cannot memorize, sir. என்னாலலாம் memorize பண்ண முடியாது, sir. Because you have no time, guys. I think you cannot derive all the equation, characteristic equation. From that equation, you cannot take one by one you cannot derive. So அதனால என்ன பண்ணனும்னா you should remember all this formula. So first we have seen damping coefficient C, damping force per unit velocity. Now we move on to what is the critical damping coefficient. Cc 2 into m into square root of s by m. So m is mass attached with the vibratory model. S is nothing but spring stiffness, and then this omega n is nothing but circular frequency of undamped vibration. And then we move on to the third formula, very important formula, damping ratio. Damping ratio or zeta. This is called zeta. Zeta equal to C by C. Already we have seen this is damping factor or damping coefficient. This is critical damping coefficient. The ratio between these two is called damping ratio. So damping coefficient, critical damping coefficient, followed by third formula, damping ratio. So these formulas and all are derived from this fundamental differential equation of a spring mass system with attached to the dashpot by equating upward and downward forces. Guys, you remember the equation, just you go through, you can easily get all the formula and all from the general solution of a differential equation given above. And then there are three different damped systems. We have over damped. So I already told you zeta. What is zeta? Damping ratio. So if you take any vibratory system, the damping ratio is greater than 1. This is called over damped or large damping. This is practically not visible. So over damping is there. What will happen here? Definitely large amplitude, infinite amplitude will be there. So it is not possible. So just 2 mark question you may expect over damped, and gate questions and all you may expect this kind of questions. So the system, vibratory system having a damping factor of greater than 1 is called over damped. So this is not a practical system since it experiences large damping, amplitude is more. Similarly, the second one is critically damped system. So zeta is 1. So in this vibratory model, both C by C is equal to 1. The ratio between damping coefficient to critical damping coefficient is 1. So actually this damper system is used to design all electrical instruments. I already told you. The property of critical damping is used in designing electrical instruments in which needles have to return immediately once readings are taken with minimum time. So immediately it will comes into distribution. Likewise, hydraulic door closer, I think you guys know that when you push it immediately, it returns to its original position, because once you open immediately, within shortest possible time, the door come to its original position, large guns and all. So return to the original position after recoiling because of firing. Once you fire it, immediately it comes into its normal position. So this is the condition. So in that system, damping factor is 1. And then under damped. Actually, normally all our present applications, I think, uses this condition only. So this is the most practical case of damping. It is also known as under damping or small damping. So by taking all the practical applications, our damping factor is lesser than 1. We are following all the vibratory procedure and all. So and then one more very important term is called logarithmic decrement. I already told you damper is attached in the vibratory model. Actually, it defines the natural logarithm of the amplitude reduction factor. So the amplitude reduction factor is the ratio between any two successive amplitude on the same side of the mean position in an underdamped system. So it is observed that ratio of any two successive amplitude in an underdamped system is always constant. So this is very important, guys. What is use of logarithmic decrement here? It measures the rate of decay of oscillations in underdamped system. So we follow only underdamped system for all our practical applications since zeta is lesser than 1. So if you attach damper, what is the effectiveness of the damper which is attached with the vibratory model? How quickly it works, and then what about its effectiveness and all is to be measured by logarithmic decrement. So amplitude means the displacement of the vibrating body for each cycle. So it goes on, so it undergoes like this. So this is the formula we have. So what about the amplitude of the starting position? So once you pull it a spring mass system, it undergoes maximum amplitude of 20 mm, and then slowly 18 mm, and then 10 mm, and then 6 mm. Finally, it comes to original position. So, how quickly these oscillations are to be controlled and then immediately arrested by these dampers? That is to be given by decrement. How far? How quickly the oscillations are to be controlled by the attached damper is given by this formula. So, logarithmic of the successive amplitude, first amplitude, second, third, fourth, like this. Finally, it comes to original position. This is the formula should remember. Initial amplitude and then amplitude after number of cycles. Guys, I think it's very important. I can exam point of view, you can really easily understand this. Generally, free third unit, free longitudinal vibration is classified into free undamped, pre-damped. So this is fundamental here. Time period, natural frequency omega and circular frequency to the square root of s by m, and then undamped natural frequency formula is f1 equal to 1 by 2 pi s by m. Just look at the vibratory model. Is there any damper? Is there? No. So what is the natural frequency formula? I already seen the formula. Now we have seen all the formula and all from the characteristic equation of a damped free vibration of a longitudinal body. This is spring, this is mass. So this is a damper attached to the vibratory system which controls the oscillation of the system. This is damping coefficient here. I forgot to write. So you should know what are the terms are. This is spring stiffness. Springs maybe are in series or parallel. Dampers are also in series or parallel. And then what are the various terminology? Very important to derive all the formula. So we are all mainly focused on the damper related parameters. What is damping coefficient? It is denoted C. What is critical damping coefficient of the damper? CC. What is damping factor? Ratio between the C by CC is called damping factor. Finally, what about the role played by damper when you attach here? How quickly it controls, and then what is the effectiveness of the damper and all is to be told by logarithmic decrement del. So look at here, just clearly differentiate these two formula. Here, without damper, what is natural frequency? Natural frequency equal to 1 by 2 pi square root of s by m, or 1 by 2 pi square root of g by del. Del is deflection, or we can simplify this formula as 0.4985 divided by square root of s. Here, look at here. I think many of the students get confused about Fn and Fd. So Fd is nothing but a vibratory body which is having damper, and the corresponding vibration is called damped free vibration. The corresponding frequency is called damped frequency. What is the formula here? Natural frequency equal to 1 by 2 pi square root of s by m. Here omega d divided by 2 pi. Omega d can be written as in this manner. These are all derived from fundamental equation. You remember, there is no other go. Square root of 1 by zeta square into omega. What is zeta? I already told you zeta is nothing but damping factor. Damping factor is nothing but C by Cc. What is Cc? Critical damping coefficient is nothing but 2 into mass of the vibratory body attached to the spring, and then circular frequency omega n. So it can be simplified as 2 into square root of s by m. So finally del. What is logarithmic decrement? 2 pi zeta divided by square root of 1 minus zeta square. Or otherwise you can calculate this del if two successive amplitude or n number of amplitudes or cycles are given in the problem. So depends on the data given in the problem, guys. So you should thorough this formula here. So in this way you should memorize the formula. Clearly differentiate what is free damped longitudinal vibration, what is free damped longitudinal vibration, what is natural frequency Fn, what is damped with natural frequency Fd, and then what are the various formulas are there in this free damped longitudinal vibrations which is closer to your damper part. Okay, one problem I'll just briefly explain you. This is asked in analytic question. I think many times this question was repeated in analytic question. So between a solid mass of 10 kg and the floor, this is floor here, this is mass. It is kept two slabs of isolators, vibration isolators. So vibration absorbers called natural rubber and felt materials are attached in series. Just look at here. Between a solid mass of 10 kg and floor, this is floor and then mass. So between floor and mass, two vibration isolators. The name itself tells you isolate the vibration. So which are in series. So both are in series. The natural rubber slab has a stiffness of 3000 Newton meter and an equivalent viscous damping coefficient of 100 Newton second meter. And then the felt has stiffness of 12,000 and then viscous damping coefficient of 330. So determine undamped and damped natural frequency of the system in vertical direction, neglecting the mass of the isolators. First, immediately you convert into a simple vibratory model. So the application, so the given application has been converted into simple vibratory model. So mass 10 kg. The two isolators are series are represented with springs S1 and S2, and then the first rubber material dampers. So here given as damping coefficient. So S1 and its corresponding damping coefficient is C1, S2, and corresponding to second damper is C2 330. So what is your ultimate aim? Immediately you convert into equivalent stiffness, equivalent spring stiffness. Here just look at springs are in series. Already we know the formula. Similarly, you know, if the dampers are arranged in series, what is the formula to determine equivalent damping, equivalent damping coefficient. So write down all the given data, S1, C1, S2, C2. Okay, guys. Now immediately you calculate S equivalent stiffness, spring stiffness, and then equivalent or damping coefficient C, F, which are in series, very simple, guys. And then we move on to what is our ultimate aim? Determine the undamped, damped. What is undamped? Fn, undamped FD. So what is undamped here? Undamped means Fn here, damped FD. So these are all the formula. So first, what is our undamped natural frequency formula? You all know that omega n equal to square root of S by M already you know. What is the natural frequency formula? Fn equal to omega n by 2 pi. What is omega n? Square root of S by M. Spring stiffness, you know. What is spring stiffness here? SEF, effective or equivalent spring stiffness value 2400 divided by mass attached to the spring system, no, is 10. So 15.49 radian per second you will get. So substitute here, you will get 2 points. So without, just look at here. So this is a mass, solid mass of 10 kg, which is there in between floor and on the top mass is there in between two vibration isolators are there in series. That is to be taken as SN, S2, and then its corresponding damping coefficient that can be taken as C1, C2. Convert in terms of equivalent equivalent spring stiffness and equivalent damping coefficient. Calculate these two, and then substitute, and then find out Fn. Guys, I think many of the students commit mistake. What is F? F is nothing but omega n by 2 pi. Omega n is nothing but square root of S by M. S is nothing but here S, equivalent stiffness. So finally, what is damped frequency? So what is formula? Fd equal to omega d 2 pi. Guys, listen here. Fn equal to omega n by 2 pi. What is Fd? Omega d, damped frequency. This d is nothing but which is associated with the damper, which is attached to the body. Omega d by 2 pi. Already you know the formula for omega d. What is the formula? 1 minus zeta square into omega n. Omega n already we know. Omega n already we have calculated in your previous step. So only unknown is zeta. What is zeta? C by cc. Already we know. What is damping coefficient? Damping factor equal to C by cc. C you know. C is nothing but damping coefficient. What is effective or equivalent damping coefficient? 76. Substitute. What is square root of S by? Already you can write cc equal to 2 into S 2 into square root of S into M. Just refer the formula here. Just refer all the formula here. cc equal to 2 into square root of S by M. So substitute here and then find out S equivalent stiffness and then multiply with mass. You will get the value of 0.247. And then omega d la substitute pannunga, you will get 15 radian per second. And then substitute here 15 divided by 2 pi, 2.38. Just look at what is the frequency, natural frequency of the given problem, 2.4. By attaching damper enna irukku paru 2.3 hertz. Damped, this is called natural frequency of damped vibration of a solid body which vibrates in longitudinal direction. Hey guys, we are assuming in only in longitudinal direction. Okay. Now we move on to second vibration called transverse vibration here. Just look at the longitudinal vibration. The vibration takes place parallel to the axis of the shaft. Just look at transverse wave. So already told you the transverse vibration act perpendicular to the shaft axis. Already we have seen. Just look at in this section we are going to derive as usual natural frequency of the free transverse vibration. Look at it's a simple shaft assumed as cantilever beam, and then it vibrates perpendicular to the shaft axis. This is a shaft axis, and then the vibration. What about vibration? Perpendicularly it acts as usual based on equilibrium method by equating upward and downward force, spring force, gravitational force acting downward, inertial force acting upward. So we are going to arrive same formula. Both are I think same formula. Natural frequency of free transverse vibration also have same formula. Natural frequency of transverse vibration is to be given as 1 by 2 pi square root of g by del. So this is same. So similar to longitudinal vibration discussed earlier. Okay. So very important part of this while solving transverse vibration of beam, transverse vibration of shaft or beam, you should know what is the deflection of. I already told you. We are going to assume. Look at here. Here this is we are going to assume this as cantilever beam. It vibrates in transverse direction. So here the beam may be the shaft or beam may be cantilever beam with point load which is acting at the end of the beam, or uniformly distributed load, or simply supported beam, eccentric point load which is acting at different points, and then uniformly distributed load or unit length. So you should understand already. You would have studied in SOM data book and all the formula are there, but you cannot take data book for exam. Anyway, you should remember what is the deflection formula for each beam. These are standard formula you should know, and corresponding frequency also given. So this is very important to solve transverse vibration. If you want to find out natural frequency of transverse vibration of beam, you should know what is the deflection of that beam. If it is fixed beam given, if it is cantilever beam given, the appropriate deflection formula you have to select and then find out the natural frequency of the beam. So just look at the natural frequency of free transverse vibration for a shaft carrying several loads. The two methods are there. Dunkerley method. So what is the formula to find out natural frequency? As usual, same formula, 0.4985 divided by square root of del. Already you know. Just look at the beam. So here, three weights are acting in the uniformly distributed load. The corresponding deflections can be del 1, del 2, del 3 for W1, W2, W3. That turned out to be calculated and then substituted, and then finally you will get natural frequency. It's a very simple problem here. Just look at, I think your faculty has solved this problem. Very simple problem. SOM and all, if you are thorough, if you know the fundamental part of solving all this SOM problems, you can easily understand. So Dunkerley method is useful to find out natural frequency of transverse vibration of various beams. We are going to assume the shaft has whether it is simply supported beam with uniformly load or the load is acting at mid and all. So another two methods are there as usual, what we have discussed in our free vibration, undamped free vibration. You no need to go in depth and all. So very important section is critical speed. So there are three different topics are there: longitudinal, transverse, critical speed. Mostly you can expect questions from the first one, damped free vibration of a longitudinal body, or in transverse vibration, either you can expect Dunkerley method, determine transverse natural frequency of transverse vibration, or critical speed of shaft. This is very important. What is critical speed here? You would have done an experiment in your lab, dynamics lab. N critical, that is critical speed of shaft. The speed at which the shaft tends to vibrate violently in the transverse direction. So at which resonance occurs. So if a circular shaft rotates at a particular speed, I think a huge noise will be there. A violent amplitude takes place at that particular speed. So that speed, at that speed, what will happen? No, resonance happens. You already know what is resonance. So the external force frequency matches with the vibrating body frequency. Obviously, resonance occurs, and then it will be broken. So we should avoid that. So that corresponding speed is called critical speed. So what are the causes of critical speed winds? Definitely it may be due to eccentric mountings of gears, flywheels, bending shaft due to its own weight, non-uniform distribution of the rotor material. I think the formula is finally we can arrive, by by taking centrifugal force acting on the beam, and then what about the restoring force? Finally, we will arrive formula to determine critical speed of the shaft. Just you go through, and then there are various observations are there. What about if omega equal to omega n? These are and all. Just you go through. I think this is the problem. I think you can easily solve. The shaft of diameter 10 mm carries at its center of mass 12 kg. It's supported by two bearings, and then the center resistance of which is 400 mm. So neglecting the mass of the shaft, considering the mass of the shaft, you have to find out what is the critical speed. So first you consider mass without neglecting the mass of the shaft. You calculate F1 equal to 0.4985 into square root of del 1. Del 1, this is simply supported beam with uniform distributed load. What is deflection formula already you know. So you find out deflection of the beam and then substitute. It's a simple natural frequency of a transverse vibration of a beam formula. So in this del 1. So according to the problem, according to the narration of the problem, so it is to be assumed as simply supported with uniform load, and then the load is acting at midpoint. So first you have to calculate mass of the shaft per meter length, and then calculate moment of inertia. So find out deflection, and then finally calculate mass of the shaft due to static deflection due to mass of the shaft, and then substitute area. So this is for neglecting mass of the shaft. Considering the mass of the shaft, so we can add these two. So static deflection due to mass, and then static deflection due to mass of the shaft. Del is and del 1, and then you will get 744. So critical speed is very important. Practice 2 or 3 problems. So some twist is there. You just carefully go through the conceptual part and then understand, and then finally calculate the critical speed for a transverse vibration of a beam. And then the last portion, I think mainly exam point of view, sometimes one 16 mark question sometimes you expect, but you thorough with these two portions. So torsional vibrations, what is torsional vibrations, sir? When it just look at a shaft which is attached to the shaft, twisted alternatively either in counterclockwise and anti-clockwise, what happens? So torsional shear stress is induced. The corresponding vibrations called torsional vibrations. So there are 3 important torsional vibrations we are going to find out. If a shaft is having a single rotor, 2 rotor, 3 rotor, what about the natural frequency? That is it. So this is a fundamental formula we can derive omega equal to Qi. Based on D-Albert principle, I already told you. Finally, we can arrive fundamental natural frequency of a torsional vibration body F1 equal to 1 by 2 pi square root of Q by I. Q is nothing but torsional stiffness. Theta is angular displacement. I think you all know that torsional equation T by J equal to C theta divided by L. C is nothing but modulus of rigidity. J is polar moment of inertia. So when the shaft is twisted and untwisted alternatively, torsional shear stresses are induced. This twisting and untwisting movements are known as torsional vibration. So this is the definition. So what is torsional stiffness Q? So in longitudinal and transverse vibration, stiffness is generally we have taken stiffness is nothing but load per deflection. Here Q is nothing but torsional stiffness. It is nothing but the torque required to produce unit angular deflection. The torque required to produce unit angular displacement. And then before, so just go through the various parameters, how it has been represented in torsional vibration, linear vibration. Just look at, if you look at displacement, which is represented in linear vibration is x, but in torsional vibration with the help of theta, we can represent velocity here omega. Here acceleration a, here alpha, angular acceleration. Here mass m. So likewise, you go through stiffness is s, this is q. F is common. F is common. Natural frequency of the torsional vibrating body is common. What is the formula? Here, instead of S by M, we have taken S by M for all linear vibration. The torsional vibration. Torsional stiffness is included and the moment of inertia is included based on torsional equation. Okay, well, so before determining torsional natural frequency of torsional vibrating body, you should know the concept, very important concept, torsional equivalent shaft. So in many applications, the shaft of various diameters at different sections are used. The shaft of varying diameter can be replaced by equivalent shaft. Just look at this is shaft with varying diameter. This is called stepped shaft. How many different dias are D1, D2, D3, D4, and then so different diameter, different lengths are there. This is called stepped shaft. While calculating torsional natural frequency of a torsional body, definitely this is to be converted into equivalent shaft in the same torsional stiffness. So how we can calculate? This is the formula. First, you take a first diameter as equivalent dia DE, and then these length and all to be considered as LE equivalent length. How you can find out the equivalent length for a stepped shaft? This is the formula you have to use it. L1 plus L2 D1 by D2 power 4 and then L3. So this is the formula you should remember for solving the problem. Torsionally equivalent shaft. How a stepped shaft is to be converted into torsionally equivalent shaft. And then there are three rotors are there, single rotor and double rotor, and then three rotor. Just look at what is the formula I already told you. Natural frequency equal to 1 by 2 pi square root of q by. Here a shaft is fixed at one end and carrying a rotor at the free end. This is called a single rotor system. So here this is called a node. Here there is no deflection. There is no deflection at this point. Zero deflection. This region is not affected by vibration. So this is called node. So remaining and all you can anti-node. This area we have vibration. So based on that we can derive equation and then we have to solve the problem. And then one more 16 mark question you may expect from these two also. Mainly in university, single and double rotor, two rotor system is asked repeatedly, I think many times. So better you focus on first part and second part, longitudinal and transverse vibration. And then two rotor system. There are two cases are there. So just to look at a shaft which is having two rotors rotating in same direction. What about its natural frequency? So just look at node diagram has been shown here. Shaft vibrates with zero frequency. System will only rotate in same direction. No amplitude of vibration at both end will be in same direction. So there is no node is formed. So here look at if it rotates, if the two rotors rotates in different directions, opposite direction. So node is formed. So node is formed. This is called node point. So this region is unaffected by vibration. Only vibration is there in at the two sides of the vibratory bone. So likewise, three rotor system also derived, guys. So with that, I conclude my session, guys. Thank you for your patience. I think you guys are feel angry. Thank you very much.
Yes, sir. Thank you, sir.
Thank you, sir. Thank you, sir.
Let Ashok Kumar.
Sir.
Yes. Yes.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you for giving valuable lecture for our students, sir.
Sure, sir.
Thank you for spending valuable time with us, sir.
Thank you, sir.
Sir, thank you, sir. Thank you so much, sir.
Okay, sir. First of all, I would like to thank Dr. Govindan, sir, for giving this opportunity to deliver a lecture. And then I also thank our beloved students. I think 7 to 8:30 is very tough time for these guys to listen this lecture, especially DOM and all. while solving classroom and all, I think they feel boredom. But anyway, thanks for your patience. I think you guys all should thorough basics, and then you solve minimum 2 to 3 problems in each category. Mainly focus on damped free natural vibration and then transverse vibration. Then it will be easy for you for fourth unit also, forced vibration. Thank you guys. Thank you,
Yes,
sir.
yes, Professor. Thank you, Professor.
Thank you. Shall I
Thank you.
leave? Okay.
Yes,
Thank you.
you can leave.
Thank you.
Thank you, sir.